Apex is a real-time streaming platform and runtime engine that enables development of scalable and fault-tolerant distributed applications. And Apex is a YARN native application. Using Apache Apex, we can process streaming as well as batch data. Using Apex, we can process high throughput and low latency applications. And we have a library of commonly needed business logic, that is Malahar library, and which is an open source. Using Apex, you can also write any custom business logic in your application. And let's move on to the architecture. We have different layers of this architecture. First, the bottom layer, we have the physical machines or virtual machines or cloud. On top of it, we have a Hadoop 2.x distribution, so which has the YARN and HDFS, which are the components of the Hadoop. Currently, we are supporting the minimum version is 2.6, Hadoop 2.6 version. So our engine will work on top of Hadoop 2.6 or more. On top of it, we have an Apex core engine, which is a real-time streaming engine, and which also have features like fault tolerance and scalable, etc. On top of it, we have a Malahar library, so which have a bunch of operators, which have connectors like input connectors and output connectors. In input connectors, we have Kafka, HDFS, JDBC, etc. And also we have output connectors also have like Kafka, HDFS, S3, JDBC. In this, we also have some processing operators like transformation, dedupe, enrichment, parsers, filters, etc. Also, we support high-level API and batch support. On top of it, we have application templates. These are app templates which are commonly used, like Kafka to HDFS, HDFS to HDFS, JDBC to HDFS, and JDBC to Kafka. This actually don't need to write any Java code. We can directly use it. And these are open source, which is under Apex license. On top of it, we have DataTorrent proprietary tools like GUI application and management and monitoring. These are used like for launching and monitoring the applications. And also we have real-time data visualization, which is used for visualizing the data for the applications. On top, we have solutions for business problems also. Now let's move on to what is Apex application. Application is represented as a DAG, as a directed acyclic graph. So which is composed of vertices and edges. Vertices is represented as operators and edges represented as streams. A stream is the sequence of data tuples. Tuple means any serialized object. And these tuples will connect operators at endpoints called the ports. An operator takes one or more input streams, performs computation, and emits one or more output streams. So here each operator is from our Malahar library or uses business logic. Now let's move on to the application example. Here you can see the green circles and the blue circles. These are the ports. And ports we are classified into two parts, like one is the input ports and the other is the output ports. So here if you see the blue circles represents the input ports and which are used to get the data from the previous operators, and green circles represents the output ports, which emits the tuples to the next operator. Based on this, we are classified the operators into three categories. Like one is the input adapter, and the other is the generic operator, and the other category is the output adapter. So input adapter doesn't have any input ports, so it talks from the external system. And the processing operators, which have the input ports and the output ports. And the next category is the output adapter, which doesn't have any output ports. This also talks with the external system, like Kafka, HDFS, database. Yeah, now see how Apex is a native Hadoop integration. Let's take a 4-node cluster. And here, the rectangles are the 4-node clusters. And once you launch an application, Apex application, this is deployed into the cluster. Then might be the cluster look like this. The green rectangles represents the operator containers. So 1, 2, 3, 4, 5, 6 are the containers, operator containers. And here 4 and 6 are deployed on the same container, which represents these operators might be the thread locker or container locker. And one of the container is the STRAM. This is a streaming application master. The job of the STRAM is monitor these operator containers and get the heartbeat of these containers. And also, if there any operator container failure, it triggers and it redeploys into the different container. And the pink rectangles represents the map reduce jobs. This indicates that our application is coexistence with the map reduce jobs. That means in the same cluster we can run the map reduce jobs as well as our application. On top of it, we have an Apex CLI, Apex command line interface, which is used for launching the application. On the right-hand side corner, we have DT console and DT gateway. These are the web UIs which are used for launching and monitoring the applications. And these are the proprietary tools of DataTorrent. So here we have used YARN is the resource manager, and HDFS is used for storing any persistent state. And these are the components of the hardware. Now, the next topic is windowing. What is windowing? Here, it's a real-time streaming platform. So the input side, the input of the real-time streaming data will distribute it into the small finite segments, chunks into the small finite segments. And these are called the application windows. And these are represented by the window ID. This ID is the window ID. And the finite small segments, as I said, that is called the streaming windows. The streaming windows is transmitted to the user, and the default value is the 500 milliseconds. And the checkpointing and bookkeeping done at the streaming window boundary. Now the application windows, we are calculating the application windows based on the multiple of streaming window size. By default, the application window is one streaming window, that is 500 milliseconds. And for the application window, we have calls to the users, operator logic, that is like begin window and the end window. That belongs to the one ID, window ID. For example, if you have an application which identifies some aggregations and emits every minute, this is your application. So here, the application window size becomes the 1 minute, that is 60 seconds. That means 120 streaming windows. The next topic is the checkpointing. What is checkpointing? Checkpointing means periodically write the serialized state of the operators into the HDFS. This happens independently for each operator, and this is a default behavior for the Apex platform. Next, what is the committed? Committed means, for example, if all the operators in the DAG have checkpointed at a particular window, then that window is called the committed window. Once the committed window calls, then we need to purge the previous checkpoints. Here an example like O1, O2, O3, O4 are the operators, and O1, O2, O3 have the checkpoints at 60, 120, and 180. 180 is the third checkpoint, and O4 is checkpointed at 60 and 120. That's the second checkpoint. So if you see here, 120 is the common for all the operators. So the committed call will happen at the window 120. The committed checkpoint number 22. By default, the checkpoint window is 60 streaming windows. Have any questions? Yeah, next move on to the main topic, the main state. Yeah, first, what is main state and why do we need that? For example, for some operators in Apex, needs the manage the large state, and that state would be the persistent storage, and it should be a distributed nature, and it should be a fault tolerant. Now here, once comes to the fault tolerant, here what happens is once the state keeps on increasing, the checkpointing of the state becomes very expensive. So this is very bottleneck for the operator. And also the other point is, if the state keeps on growing, at one point it goes to out of memory. So these are the couple of issues we are facing in the operator. So the solution for that fixes issues is the incrementally the checkpoint. That means a checkpoint, instead of saving the complete state, will save the difference between the two checkpoint state. So these are a couple of use cases for using the main state. One is the deduplication. Here, for example, if I want to duplicate the separate out the duplicates from the data set which needs to be like two days of data, which have the 2 days of data, we want to separate out the duplicates. So for the 2 days data keeping it in the memory is a very bottleneck for the platform. So here we'll use the many state. Many state have a technique. Instead of memory, it will save into the disk. The similar one more use case is join operation. Join the two streams based on the specified condition and emit the join data. And here also, if you want to join like for 2 days or 3 days, some X days data, so we need to store that X days of data into the store. So in memory, here also in memory is a bottleneck. So we use the main state. In the next slides, we'll see what is main state and what are the components and how it will achieve the best for these use cases. Yeah. Next, move on to the what are the components of the main state. The first, these are the pluggable components to the main state. So the first one is the buckets file system. The job of the buckets file system is manage the buckets for reading, writing, and deleting. And these are the time buckets on. And the next is also it updates the buckets and the file metadata. And the next component is the checkpoint manager. So here we'll use the incremental checkpoint manager. So instead of saving this complete state, we'll save the difference between the two checkpoint state. And we'll save it into the one file. That file we'll call it as a window file. And later we'll transfer this window file to the bucket files. The bucket here, bucket files is the time bucket files. Means we'll distribute it based on the time field. And the next component is the time bucket SNR. The job of the time bucket SNR is to manage the length of the time buckets and also the time boundaries, and also specifies the keys or belongs to which of the time buckets. Once the boundary is moving, it also manages the time boundary, sliding time boundary. And the next component is the state tracker. The job of the state tracker is tracks the size of the data in memory. Once the size crosses the available memory, once it crosses the available memory, it requires the buckets to free the memory. And this is the soft condition, it's not the hard condition. And the next component is the file access. Is the layer for the file system. And here default the value used is DT file, which is same as the Hadoop T file with a different reader implementation. Due to that different reader implementation, we have a faster access for the random values, random keys. Now let's move on to the next component. It's a bucket. Here the bucket is group the events. and we call these buckets as the key buckets. And it's further divided into the time buckets. On the right hand side, you can see the key bucket, and these are the time buckets. In key bucket we have different layers. One is the memory layer and the other is the disk layer. And in memory we have different components like flash data, checkpointed data, committed data. So all these are in memory. And the disk components, like we have time buckets. So whenever we insert a key into the bucket, first it saves into the flash data. And at every checkpoint, the data moves from flash to the checkpointed. And also at the same time, it flashes the data, all the buckets are persisted in a window file at every X number of windows. Here, by default, the X value here is the checkpoint window count. That is 60 streaming windows. And these files are named with the window ID. And at every committed, the data moves from checkpointed to committed. And also, if all the window files till this committed window are saved into the data files. This data file means the time buckets. So at the point of checkpoint, we have the window file, and at the time of committed, we have the data would be in the committed and as well as in the time buckets. Let's say, for example, the value of X is 10. That means at every 10 windows, we need to write the data onto the window file. And the checkpoint window count is 5. Now, for example, currently at window 31, the data files are at 10, 20, and 30. These are the data files. And at committed, if committed will happen at window 25, then these data files will transfer into the bucket data files. After it is written into the bucket data files, it purges these window files. Let's say here at window 35, you have the window files like 30, 40, and 50. At the same time, if the committed is happening at 45, then the window files 30 and 40 will transfer into the bucket data files. Once the transformation is done, then it purchases the window files from the HDFS. Now here see it's a sliding time buckets. These time buckets are depends on two parameters, two configuration parameters. One is the bucket span time and the other is the expiry period. The top level is the bucket IDs, and the bucket indices is depends on the expiry period and the bucket span time. For example, if the expiry period is 20 seconds and the bucket span time is 5 seconds, then the number of buckets is 20 by 5, that is 4. So these 4 time buckets will exist. Once the future key inserts into the bucket, that means that the tuple might be belongs to the bucket time bucket 4. Then this would be active, and the older bucket, that is the time bucket 0, will be expired. So this is the sliding time buckets. So this happened the slider. Yeah, sorry. The next topic is how do we store the data into the bucket? Here the bucket is the key bucket. Let's go through this example. Here I have the fields like key, time in seconds, and window ID. And the other two things are like window data files and the bucket data files. Here the assumption is the value of the bucket span time is 5 seconds and the expiry period is 15 seconds. So the number of time buckets here is 15 by 5, that is 3 time buckets. And the default the value of the checkpoint window count is 5. So at every 5 windows, it writes the data into the window data file. Now let's see here the example. First, the key 4 comes at window ID 1 and the time in seconds is 1. So at this point, first it inserts into the flash, that is in memory segment of the key bucket. And the next key is the 5 with window ID 4 and the time field of the key is 3 seconds. This also inserts into the flash segment. And the next key is 12 with window ID 5. Sorry. With the time in seconds is 3. This key is also inserted into the flash segment. And the 5 window is the checkpoint window. So it creates the window data file with 5 and all these keys are saved in this window data file. And also This flash segment, the data which is in flash segment moves to the checkpoint segment. And the next one is 3 at window ID 7. And the time in seconds is 6. So first this saves into the flash segment here again. And the key is 6 at window ID 10. The time is 10 seconds. This also saves into the flash segment. And 10 is the checkpoint. So these two keys saves into the window file 10. And here it calls that committed, for example. That means then we need to transfer this window of data files to the key data files, as shown here the diagram. As you see here, 0 to 4 seconds belongs to the 0th bucket, and 5 to 9 seconds belongs to the key time bucket 1. And here 4, 5, 12 are in between 0 to 4. So this data is in this time bucket file. These are the files, again, time bucket files. And
Hey guys, Vikram here. So I think Charan has asked a lot of questions right now, but probably I think it's good to have those questions at the end, and so just stick around till the end. Thanks.
these files are the DT files. So it saves into the sorted order, so that if you fetch any particular key, it gives very fast results. And the next one is 22 at window ID 13. So the time is 12 seconds. So this saves into the flash segment. And the next one is the check. And if 15 at the checkpoint, then this data is saved into the window data file 15. And the next one is the key is 16 at window ID 18. And the time for the key is 17 seconds, for example. Then this saves first into the flash segment. And the next one is 20 is the checkpoint window. So this data saves into the window data file 20. And for example, if this is the committed window, then this window data files will transform to the key time data files. And here if you can see, the 22 belongs to the 10 to 14 time bucket, and 16 belongs to the time bucket ID 3. Once this is completed, this time bucket is completed, then it purges this time bucket. This way the store will happen into the key bucket. Now let's see how to fetch the data from the bucket. I took the same example. So at this point, if you see at this point, the keys 3, 6 are in the flash segment, and 4, 5, 12 are in the checkpointed segment. And there is no data in the committed, and there are no time buckets. because till this point the committed call is not yet happened. Now, for example, if you are searching a key, here how will happen is the searching. First, it searches into the flash segment. If the key is not present in the flash segment, then it looks into the checkpointed segment. If the data is not present in the checkpointed segment, then it looks into the committed segment. And if the data is not present in the committed segment, then it looks into the time buckets. If not, it returns the null value. For example, if you are searching a key 12, so first it searches into the flash. So the key 12 is not present in the flash. So it checks into the checkpointed segment. The key 12 is present in the checkpointed segment, it returns the value. For example, if you are searching a key 9, first it checks into the flash. 9 is not present in the flash, so it checks into the checkpointed segment. Here is also not present. Then it checks into the committed. The committed segment is empty. Then it looks into the time buckets. But the time there are no time buckets, so it returns null. This way, this fetching will happen. Let's look up into the last one. Here, at this point, 16 is in the flash memory and 22 is in the checkpointed. 4, 5, 12, 3, 6 is in the committed segment. In the same way, 4, 5, 12 is in the time bucket 0 and 3, 6 in the time bucket 1. This is the state of the key bucket. Now, for example, if you are searching the key 12, first it searches into the flash segment. So the data is not present in the flash segment, then it looks into the checkpointed segment. The 12 key is not present in the checkpointed segment, then it looks into the committed segment. Here the committed segment, the value is there, so it returns the value. What will happen after some time, the 4, 5, 12, 3, 6 are the keys are in disk. So the main state deletes this case at some point. Then the 12 key looks into these time buckets. So this way the fetching will happen from the buckets. Now we have a different implementations of managed state. The first implementation is managed state implementation. Here, the system time corresponding to the application window is used to subgrade the keys. So that means we don't need to, if even the tuple have the key, it ignores and it uses the system time. And here the data written on the disk in this format, the base path and what's the key bucket ID, and then the time buckets. So the number of key buckets is calculated from the number of buckets. And the number of time buckets we categorize from the expiry before and bucket span milliseconds, which we have seen in the previous slide. So these are the methods for writing or reading the data from this state. As you seen that we didn't pass any time field here. So only the bucket ID, here the bucket ID is the key bucket ID. So we need to pass the key bucket ID, key and value. For fetching, we need to pass the bucket ID and the key. Now also we have a asynchronous method for fetching. And the next implementation is manage time state implementation. Here, the time bucket is derived from the user provided time. Here also the data on disk is saved in the format of key bucket / time bucket. And the number of key buckets is calculated from the number of buckets parameter. And the number of time buckets is calculated from the expiry before and bucket span milliseconds configuration parameter. And below are the methods for reading and writing the data from the state. And here if you see that for inserting the data, we'll pass the bucket ID and the time. So here bucket ID is the key bucket ID, and this is the time of the tuple, and key and the value. And below two methods are the fetching the keys from the bucket. The next implementation is manage time unified implementation. Here, the time bucket is derived from the user provided time, and these are the main buckets. That means here there are no time buckets. Sorry, there are no key buckets. The time buckets are the main buckets here. So the data written on the disk as in the format of base path, and there are no key buckets here. So it saves into the operator ID / the time bucket ID. As I said in the previous slide, the number of time buckets is calculated from the expiry before and expiry span milliseconds configuration parameters. So here there is no key bucket. So the below these are the methods for writing and reading data from this state. Now, how to use the manage state in the operator? Let's look up here this example. So I want to implement and map operator. So my map, which implements the operator and the checkpoint notification listener, as this is the for the checkpoint and committed calls. So here I have a store manage state implementation. This is the first implementation, first type of implementation. And have a transient cache, which is a map of slice, slice. So for this, the put will call first its inserts into the cache. So here the constraint of this manage state is once all the fetching is done, then only you have to insert into the state. That's why for inserting first we are putting into the cache. And for fetching the key, here first we are searching into this cache, in memory cache. If the key is not present in this cache, then it looks into the store. And if you see here at the end window, whatever the keys we are inserting, those we are putting into the store. And at the end, we are clearing this cache. So after all the fetching is done, then only we are inserting the keys into the store. So this way we can use the main state in the operator. Now let's look up into the what's the summary of that main state. So it's a persistent key value data structure, and it's a fault tolerant, and it's a distributed, and also have asynchronous reads. So it reads from the loading data from the disk. And also have a configurable cache depends on memory limit. This is the limit we used it for clearing the data in the buckets. Once the memory size of the bucket, size of the state crosses this limit, then we clears the data in memory buckets. And it's an incremental checkpoint. We have scalable data structures, and the backend of this data structures is the main state. So we can refer these data structures from the Malhar library, or scalable maps, scalable list, etc. And these are the few resources about the Apex and the DataTorrent. Just have a look up these sites. Yeah, that's it from my side.
Thanks, Chaitanya, for the wonderful session. So I think we have a couple of questions here. Uh, so, so we'll just go over each of these questions one by one, and so Chaitanya will try to answer them. Yes, these slides will be available online. So I think after this meetup, even this video will be uploaded on the YouTube, and the slides will be shared with you. So guys, so we have one question. Actually, we have four questions from Charan. So we'll go over them one by one. So one of the question Charan has asked, can I have a streaming window account every event if I want the aggregation to not wait for the 500 millisecond batch window millisecond batch window size, but keep counting as events stream in. So the I think the window size is kind of configurable. So you can have your own window sizes. So whatever is the window size you want to provide, you can actually provide through the configuration, and then it will the Apex platform will do the aggregation on that window size. Again, if you are not so I think 500 millisecond window size batch window size is like kind of a default uh, configuration, and so Apex don't really work on the window sizes, but it's more of on the each tuple is processed independently. But for doing an aggregation, we need to know the which window it belongs to. So that's the kind of significance of that. The second question Charan has asked about visualization, whether he can write his own Angular app and query the Apex for the streaming data. So as of now, we don't support that kind of functionality. So you can write your own Angular app and provide your visualization probably in D3 or something. Um, so you want to answer the next question?
Hi, the next question is in terms of crash recoverability, assuming Kafka input to checkpoint gets state gets distorted and remaining events replayed from the Kafka source. Does it support Kafka exactly once processing to updating main state? To clarify this here, just have a look of there is an example Kafka exactly once from the demos library. Here we didn't use any main state backend of the Kafka. We just saved those offset manages on the HDFS. We didn't use the main state as a backend of the Kafka. Yeah, let me know if you have any questions.
So guys, do you have any questions on this particular session? Or you can actually connect with us on offline as well. If you have any questions as of now, we would be happy to answer whatever the questions you have. Uh, so we'll just wait for a couple of minutes. If you have any questions, you can type it here, or after that we'll just close the session. Thank you for attending the session. Yeah, so I think there's no more there are no more questions actually from the audience. So so we'll be closing this session now. So thank you for attending, and please look out for the more sessions on the on Apex itself. Um, so thanks once again. Thanks for attending.